All right, so vectors on a plane, just some properties here. So we're going to let u equal to the component u sub 1, u sub 2. And v, we're going to let it be also a vector with components v sub 1 and v sub 2. Okay, so we're going to let that be the case and let c be a scalar. Now remember, scalar means constant, right? We're just not using the word constant because we don't want to mix it up with physics terms. So here are the definitions. So the very first one is if you get vector u plus vector v, then your result will be u sub 1 plus v sub 1, comma, u sub 2 plus v sub 2. So you can add vectors, just add their components. So I guess you could call it the x component, add those together, add the y components together, and that's your sum of your vectors. So again, not a very hard thing to do. Now there is scalar multiplication in a vector. So if you have c times vector u, then your result is cu sub 1, comma, cu sub 2. Which, by the way, works both ways. If you notice that you have a vector component, let's say your vector is 5, comma 10, you can actually factor out a 5 and write 5 times the vector 1, comma 2. And that's equivalent. Okay, you can actually factor out of vector components, not like points. You can't just factor out of points, right? But out of vector components you can, because you can multiply into, that means you can factor out of. You can get a vector, okay, and multiply it by a negative, which is kind of weird that they put this as a property, because property number 2, I mean, what's wrong with calling c negative 1? But they want to write an extra one here. Now, just so you know, the negative vector has the opposite direction. Okay, so let me write that right here. So the negative vector has the opposite direction. So if the vector is pointing in a 45-degree angle in quadrant 1, then the negative vector would be in quadrant 3 pointing at a 45-degree angle, which would be, what is that, 225? Okay, so it's just flipping to the other side. And actually, you know what? Let's not do a 4 here. Do me a favor. For number 1, just put a minus under here, because the fourth one just says that you can subtract them. So we'll just put plus or minus up there. Okay? And we don't have to write so much for those. So you can add or subtract, it doesn't matter. It's just based on the components. So let me give you an example that we can do really quick. Is this example 3? Yeah, I think it is. So given the following vectors, okay, so vector v is negative 2, comma 5, that's its component form, and u is 3, 4. Then for part A, let's find half of vector v. For part B, we'll find u minus v, and for part C, we'll find v plus twice u. Again, this is not like super difficult. Just half of v means you can multiply half into your vector component v, right? If v is negative 2, comma 5, if you multiply half into it, your result is negative 1, comma 5 over 2. And that's it. Okay, it doesn't get much more difficult than that for part A. Part B, they just want us to subtract vector u minus vector v. So go to the first component of u, which is a 3, and the first component of v, which is a negative 2, and subtract them. So 3 minus a negative 2, that's a 5. And then do the same thing with the second component. So 4 minus 5, that's negative 1. Like I said, the examples today are pretty easy. They're not too bad. And then part C, they want v plus twice u. So what I'm going to do here is I'm just going to kind of give us a little bit more info in a sense of like making it easier for us to keep track of things. So I'm going to double vector u. So that's 6 comma 8. All right. So that's what they want me to do. Vector v plus twice u. So there's twice u, 6 comma 8. Now just add them together. This would be 4 comma 11, right? No, 13. Sorry. 4 comma 13. So that's that example. So that's applying the vector component, addition, subtraction, multiplication, etc. That's what they're wanting us to do. Now, there's two quick theorems, which we're just going to call them definitions here. One of them is the length of a scalar. Of a scalar multiple. So if we let v be a vector and c be a scalar, then the magnitude of c times vector v is the same as the absolute value of c times the magnitude of v. So in other words, you could just find the magnitude of the vector and then multiply it times the absolute value of c. Okay? So if it was a -5 times vector v, and you're finding the magnitude, then at the end you're going to have whatever the magnitude of v is times 5. Okay? Not times -5, but times 5. So that's one of the definitions. And the last one for today, the last definition, is the unit vector. So the unit vector in the direction of v. Or vector v. A lot of times, whenever you find a unit vector to a vector, number one, its magnitude should be equal to 1, because that's why we call it the unit vector, because its magnitude is 1. But more importantly, the vector that you find, this brand new unit vector, has to be in the same direction. In other words, it has to have the same slope or the same angle, whatever it happens to be, right? So that's why they say it's the unit vector, but they say in the direction of v. So if vector v is a non-zero vector, because remember, if it's a zero vector, it has no direction, it's a point, okay? Then vector u, which will be equal to vector v divided by the magnitude of vector v, okay? So that has length of 1. So in other words, if you want to find the unit vector to any vector, you get the vector and divide it by its magnitude. So in other words, let's say that the vector was 10, 20 and the magnitude was 5, then the unit vector would be 2 comma 4. Okay, if that were the case. Okay, so just use whatever vector they say, hey, can you find a unit vector to this vector here? Well, you get the vector and divide it by its magnitude. Okay, each individual component divided by its magnitude. So this is something we'll worry about later. Okay, so it has a length of 1 and it has the same direction as v. And the same direction as vector v. So if you're wondering, like, is that true? Well, think about it. If the vector 10, 20 is given to us, then the direction of 10, 20 is just the change in y or the change in x, 20 over 10. So the slope would be 2. Well, the unit vector we found was 2, 4. So 4 over 2 is also 2. So they both have the same slope, right? The magnitude of this would be, like I said, it's going to be considered a unit, right, for us. But I'm not saying that this is going to work out properly to what we need to do, but the idea of it is there. So we're just going to basically be able to find our values for this using that formula for a unit vector, okay? So again, if you use that formula, you know that's going to have a length of 1. U will have a length of 1 and same direction as V. So sometimes instead of saying a unit vector, they might say to normalize a vector, okay? So let me put that right here. Sometimes they refer to this as a normalization of V. Excuse me. All right, so standard unit vector. We're going to say the vector 1, 0 and 0, 1 are called standard unit vectors. Okay, and they label them like this. I is 1, 0 and J is 0, 1. Some people think of it like as the X component and the Y component, okay? I and J. So let me put right here, note, if vector V is V sub 1, V sub 2, then vector V, we can rewrite it like this. I know it's going to look a little weird, but all I'm doing is just kind of making it into like a sum of two vectors, right? So if you put those together, you do get the thing up top, okay? Now, notice if I factor out V sub 1 from the first one, I get 1, 0. And if I factor out V sub 2 from the second one, I get 0, 1. And 1, 0 and 0, 1, those are I and J. So vector V is V sub 1 I plus V sub 2 J. Okay, this is called a linear combination. So linear combination. So when they break down the vector into its components and include the unit vectors, that's what they call a linear combination. So we're just going to do a real quick example on that, and then we're done. I'll put it right here. Example number 4. Let U be a vector with initial point 2, -5 and terminal point -1, 3. -1, 3. Let V, vector V, equal to 2I minus J. So notice the vector form for V would be a 2, -1. Okay, that would be the vector form. Okay, 2, -1. If you write 2, -1 in linear combination, it's 2I minus 1J. All right, so we're going to let that be the case for vector V. So write the linear combinations for And here's the first one. We'll do U. The linear combination for U. Now, to find the linear combination for U, the very first thing you got to do is convert those points to a vector, right? So you're going to get the x components and subtract them. So we'll go terminal minus initial. So -1 minus 2, that's -3. And then 3 minus a -5, that's 8. So the linear combination would look like this. -3i plus 8j. So that's not too bad, right? Just create the point, rewrite it in the right format, and that's it. So that's the first question. B, if W is equal to 2U minus 3V, they want a linear combination of that. Okay, so you might want to kind of do it this way. 2 times -3i plus 8j minus 3 times 2i minus j. Go ahead and distribute. It works just like that. It's not a big deal. So -6i plus 16j minus 6i plus 3j. And then just combine your like terms. So the i's go together, the j's go together, so you end up with -12i. Yeah, it's -12i plus 19j. And that's vector W in a linear combination. No homework. Well, actually, I'm gonna look. If I decide it's gonna be stuff like this, nothing like, oh, here's a word problem. Okay, it'll be something simple. That way, maybe you can at least do a little bit of the homework, and then when we get to the word problems, maybe you don't have to worry about it. Okay, but I'll figure it out and see if I include that in your email.